welcome to the latest video in your Design of Experiments course. Now in the last two videos what we've been looking at, we've looked at the orthogonal pattern, the center of a designed experiment. We've then looked at how the software will deal with the orthogonal pattern and then turn it into a coded pattern. So we know now that the DOE pattern is the right pattern to do always. It's the pattern that will get the maximum amount of information from the minimum amount of data. So what we're going to do in this video, we're going to take a look at a simple analysis for a little two-factor, two-level problem. So we're going to imagine maybe it's time and temperature. So we're going to take a look at that. I'm going to build the pattern on the board. I'm going to write the data in there and I'm going to show you how the analysis works. The way that the analysis takes one block of data and cuts it up in multiple ways. That's what makes DOE so efficient. So let's get the pattern on the board. Let's take a look at this thing. So okay, look, we got two factors. We got A and B. Now, of course, we're going to be in the real world. So A and B are going to be in real units. Time, 5 and 10 seconds. Temperature, let's put it in a different color, I think. 70, 90. Okay, that's what you're going to do. You're going to do, let's write it up here, look. Two factors, two levels, that equals 4 combinations, 4 runs. There are the 4 runs. So you're going to set your system up. You're going to put those 4 combinations in and you're going to collect data. Okay, so the data that you're going to collect is going to be around 40 data points. And the data is going in there. Okay, so that's what you're really going to do. That's the practical. Now what's the computer going to do? Well, what the computer's going to do is to turn that pattern coded so it looks like this. You've got A, you've got B, and it will add the A-B interaction in there. You'll never see this though. You'll never see this column. So it's going to go minus, minus, plus, plus. By the way, I've dropped the 1 just purely for simplicity. You know that 1 comes after the sign, so it's always going to be a 1. Minus, minus, plus, plus. And of course, it's minus, plus, minus, plus. This is the coded pattern. To get the A-B interaction, we multiply these together. Symbols are the same. It goes positive. Symbols are different. It goes negative. So the computer, this is the computer world now. It's working with that pattern. And the analysis that we're going to do is with that pattern. So let's assume that we've done the DOE, we've collected the data, and then what you do is you take your data points across row 1, you work out the average. You take your data points across row 2, you work out the average all the way down. Now, you can also do the same thing for standard deviation. So in here, if there's 40 data points, there's obviously going to be 10 data points across here. So you work out the standard deviation for the 10. I'm not going to do those in this little example, but that's what would happen. So you would have a column of information, which is the average result. You have a column of information, which is the standard deviation result. They're the two things we're trying to transform. We're trying to transform the physics of the process. We're trying to control the physics of the process. We want to make the process very repeatable by controlling standard deviation. Then we want to take that repeatable result and drop it on the target using this knowledge that we're going to get here. Okay, so we have our data. Let's do the analysis. So what the analysis is going to do is this. We're going to take this column of data and cut it in 3 different combinations to get 3 bits of knowledge out of the same data. That's why the DOE is so powerful and fast. So here we go. What was the average when A was set low? So A was set low at 1 and 2. What was the average of those 2 results? So what's that? 35 over 2. That goes to 17.5. First bit of analysis. Next question. What was the average when A was positive? Again, these 2 results add up to 35. 35 over 2, 17.5. And the delta, the difference between these 2, is 0. Okay? So that was 1 and 2 versus 3 and 4. That was the first combination. Now what we're going to do is change the combination. We're going to go 1, 3 versus 2, 4. So we're going to look at what was the average when B was low. These 2. 25 and 25 over 2. Well, that's easy. It comes to 25. When B was high, what did we get? These 2. That's 10 and 10 over 2. I can work that out. That's easy. That's 10. And the difference between these 2, minus 15. We're always taking the low value from the high value. So the delta there was minus 15. What that means, of course, is when you flick that switch backwards and forwards, you drove the result down. That's all it means. Whereas if it's a positive number, you drove the result higher. And finally, let's work out the interaction. When the interaction was low, those 2 middle values there, 35 over 2 is 17.5. And finally, 1 versus 4, these 2, 35 over 2. Now, by the way, this slide is in your notes. It's there, it's empty. If you want to follow along, I forgot to say this at the beginning of the video, but if you want to follow along, you can complete this table. So if you want to stop the video now, take a look at the table. Put the pattern in, put the coding in, put the results in, and you work out this table. You get those results. That would be a great thing for you to do now. So there are the results. Away you go if you want to do that. Now this is the basic information. Now we can do 2 things with this information. We can draw a picture. So remember the pizza exercise where I drew those pictures, marginal means plots or factorial plots if you use Minitab. So marginal means plot. What does the marginal means plot look like? So it's a graph. To put a scale on, 10, 20, 30 up the side. We've got A at the low, at the high. We've got B at the low, at the high. We've got the AB interaction at the low, at the high. Okay, let's plot the graph. 17.5 against 17.5. So where's that? It's about those 2 data points there. Put the 2 points, join the dots. Then what we've got is 25 to 10. So B at the low gave us a result of 25. B at the high gave us a result of 10. Plot the points, join the points together. And finally, the AB interaction, 17.5 place 17.5. Join the dots. This is known as a marginal means plot. Now, everything I did with this column, I could have also done with this column. So what we're seeing here, look, is B is driving the average result. B is driving the process backwards and forwards. If we analysed S, maybe something else is driving S. We'll have a look at that when we use the computer now. So we'll see that in a moment, but we'll use the computer and we'll do an analysis for Y and for S, and you'll see all this analysis play out in the software. So we've plotted the marginal means. We've got a very simple view of what's going on at the moment. But now what I'm going to do, I'm going to take that information and I'm going to create a model for this process, a mathematical model. Now the template for the model looks like this. Y hat, which by the way just means predicted. The hat just means it's a prediction. Y hat equals the grand mean. That's the average of this lot here. So the average of this lot here is actually 17.5. So I'm just going to squeeze that in there. So the grand mean of that column, 17.5. So Y hat equals the grand mean plus the delta for A over 2 plus the delta for B over 2 plus the delta for AB over 2. So there is the empty template. Now what we're going to do, of course, is enter the information that we've got, this number and these three numbers, and we'll create an equation using that. So it goes like this: Y hat equals the grand mean 17.5 plus 0 over 2 for A minus 15 over 2 for B plus 0 over 2 for AB. So there's the base equation. What I'm going to do is remove all the nonsense and just get the equation as it should be. And the equation falls out to look like this. I'll put it over here, I think you'll see it better. Y hat equals 17.5 minus 7.5b. There is the equation for your system to move the average. So there's the equation, okay? So now, of course, if I move B up and down, I can work out this little term and it'll give me a prediction value. Now obviously I went from 10 to 25, so that's sort of the maximum as the limits of where I tested this system, between 10 and 25. But if somebody said to me, Paul, can you hit 22.3 for me? I can ask this equation to resolve to 22.3. In other words, when a customer says, can you hit 22.3? I'll go, yeah. If the customer says, can you hit 18.1? I'll go, yeah. If the customer says, can you hit 24.9? I'll go, yeah. I can resolve this equation to any value I want. Obviously, if the customer came along and said, can you hit 27.8? I'll go, no. I already know that. Imagine that. Customers come along all the time. Marketing comes along all the time. They love to say we want the best piece of equipment for the cheapest price, and they want ridiculous performance numbers out of your systems. And you try and please marketing, but at no time do you get the data that definitively says this system won't go to 27.4. This will tell you. This will tell you that knowledge. You can tell marketing, clear off, the physics is not in our favor. Okay, so this is knowledge, you know. We've got that knowledge, but then the way you use it, of course, well, that's wisdom. I can't give you wisdom. I can only give you knowledge. Right, now let's take a look at the same analysis on the computer. We're going to get the software to do this. Now, I've already set the pattern up, so the numbers are already in there. I'm just going to show you how the computer generates the marginal means, generates the equation. We'll also look at the fact that it'll do the same thing for S. So let's take a look at the software doing the same analysis. Okay, so here we are, look. SigmaZone has set this up for us. So it's set up the pattern on the left, 5 and 10, 70 and 90. We've collected the data in the yellow fields. Now I've only got 3 data points per row. This of course should be closer to 10 data points per row. I kept that number down just purely to keep this on the screen and make it really easy to see what's going on. And then you can see, look, 25 and 10, 25 and 10 in the green column. So that's what we've just analysed, and then we've created that equation, 17.5 minus 7.5b. You can also see, though, that the computer has worked out the standard deviation for you. So there's a column of standard deviation. That's what the S column is. So we can also see how standard deviation is affected by the experiment that we conducted on our system. Let's do the analysis that we just did by hand. SigmaZone, analyze design, marginal means plots. Click on that. Now it says, what plot do you want? Do you want the Y, the S, or both? Well, why don't I ask for both and click OK. Now the first one that it shows me, it always defaults to S. I'm going to go back to Y so we can see the one that we drew. Here's the one that we drew where we said B, factor B is the one driving the result. And if you remember, the top point, the average at the low, we got it to 25. You can see, look there, I've pointed at it. What's the value? 25. The average then at the high setting came to 10. That 25 to 10 value, and we drew that by hand on the graph. There it is. So that's how Y is being affected. The mean is being shifted by B. But the mean is also, the standard deviation is also being driven by B. So we don't want high standard deviation. That's a very inconsistent result. So the more that you tend towards 90 for the temperature, the more you will drive the process to be inconsistent. The more you tend towards 70, the more you will make the process consistent. Now that's going to create a complicated situation for us because B is driving both the mean and the standard deviation. Okay, so that's our first analysis. There's the marginal means plot. Now what we're going to do is go back to the data, back to SigmaZone, analyze design. Let's get the equations. Press multiple response regression at the top. Now you get this table. Now to explain what the table is, on the left is the Y hat equation. On the right is the S hat equation. In the middle is a prediction window that is joined to those two equations left and right. Okay, in the yellow values at the moment, we have the two factors set to their mid value, 7.5 and 80. And then you can see down here, we have two results in the green fields. We have the two results in the green fields. 17.5 is the average, and 0.37 would be the standard deviation if you use the two values in the yellow fields there. That is how the software is working. So let's take a look on the right. First of all, we need to find our equation. Well, there is the equation. There's the equation we worked out. The constant, look, is 17.5. A returned a delta of 0. B returned a delta of minus 7.5. AB returned a delta of 0. There's the equation. Y hat equals 17.5 minus 7.5b. There it is. Let's go over on the right hand side. Look at the S hat equation. S hat equation is a little bit more complex. Look, there's a bit more going on in this one. But the S hat equation, look, is S hat equals 0.37644 minus 0.05 for A, plus 0.22644 for B, minus 0.001 for the AB interaction. There's the equation for S. Now, as I said, I can ask both of these equations to resolve to a value. I'm going to ask the computer to hit a value now. So I'm going to go Sigma Zone, Graphs and Optimization, Multiple Response Optimizer. Now in this window, it's just asking me to confirm, are those variables continuous? In other words, can I set time to 5.36 if I wanted to? In other words, anywhere between 5 and 10. So if I leave the check mark in there, yes, it's a continuous scale. So I'm going to click OK to that. The next window I don't use, so we're just going to click OK and click past it. And then we get the optimizer window. Okay, and it says, what do you want to do? And it says Y hat. So I want to optimize Y hat. And I don't want to maximize it to 25. I want to go equals, look there. So if I set equals to, it opens up a little window and I can just ask it to hit a number. So let's have a think. Where shall I ask it to hit? 22.5. So I'm asking it to hit 22.5 and then I have to click, add that as an objective. Then I'm going to ask the computer to hit that value, optimize. And it comes back and it says, well, if you put A to 5 and you put B to 73.33, you will optimize this process. If I click Settings to Worksheet, it pops those two values in the yellow fields, and then in the green fields at the bottom, it tells me the prediction. You will hit 22.5 with a standard deviation of 0.27. And that's how Sigma Zone does the analysis. Okay, now that's the first time you've seen that, so we're going to use that again and again. There's a little bit more to what you've just seen there. I've literally just shown you the basics of how we drew the marginal means, the basics of how we drew the equation. But when you get process knowledge, you can play tunes with your system that you just will not get from any other piece of knowledge. So for example, in this equation, we know time makes no difference. Time is not part of our problem. It's not part of our control system. Well, if you have a manufacturing plant where the speed of the manufacturing plant doesn't matter to the quality of the outcome, What are you going to do to it? You're not just going to ignore this column and go, all right, look, time doesn't matter. Let's forget it. Let's change the temperature. What are you going to do? Well, you're going to set the speed to 5, aren't you? Because you're going to make more money. So we can make a good product as fast as we like. By the way, within the window that we tested, really important. Just because we said 5 and 10 makes no difference, it doesn't mean that if we went to 2.5 seconds on the cycle time, that would make no difference. We didn't learn that because we didn't test that design space. So you've got to be careful. We can work within the window. What did we learn? 5 to 10 makes no difference. Process goes to 5 and we make more money. Fantastic knowledge. And then you can make the quality or the target that the customer asks you to hit by just tuning the temperature to the right value. That's the knowledge that's come out of that simple 2 to the 2 experiment. It's knowledge you would never get with a 1-factor test. And even if you did get the knowledge with the 1-factor test, it would have taken you double the amount of flipping effort, because you would have had to done 40 for A and you would have had to done 40 for B. So it would have taken you 80 data points, not 40 data points. And of course that gets more complicated if you add in a C, a D and an E, because when you add in a C, a D and an E, a DOE sticks at 40 data points, it doesn't move. Whereas when you go A, B, C, D, E, you go 40 for A, 40 for B, 40 for C, 40 for D, 40 for E. Your testing is growing exponentially. Of course you don't see the interactions. You're working 5 times as hard and you're not collecting as much information. That's why we do a DOE. It's always going to stick around 40 data points, and this information is always going to pour out of. This is a full factorial modeling DOE. That's what we've just done. We're going to show you how to model. We're going to show you how to screen. Screening, by the way, is the technique that the vacuum cleaner designer is going to use. And we're going to take a look at the screening DOE of choice in the next video. See you next time.